picking up where we left off on selection rules for single electron atoms or hydrogenic atoms, let's just write down what the selection rules are for multi-electron atoms. And these are carried out in very much the same way by working through the entire wave function of the system in order to set a non-zero dipole. And because it's a complicated set of functions to work through, we won't work through them in detail, but take my word for it when I say that we can set out the selection rules. So the multi-electron selection rules are very similar to the single electron rules. You have that delta capital S, which recall that's the sum over all electrons of the individual spins, has to be equal to 0. Delta L, which again is the sum over all individual angular momentum quantum numbers, has to be equal to, in this case, 0 or plus or minus 1, as well as the above. In that delta Li for an individual electron has to be equal to plus or minus 1, and delta Mi has to be equal to 0 or plus or minus 1. You also have that delta J, capital J, which is equal to the sum over all Li plus the sum over I of Si, has got to be equal to 0 plus or minus 1, except J equals 0 to another J equals 0 state. Now that is allowed. So putting all of our selection rules into practice, let's just look at the hydrogen atom, the simple case, the single electron, the example for hydrogen. We might have in the ground state, so this is n equals 1, n equals 2, and n equals 3. And in the ground state, you can have a 1s electron, you can have 2p, and in the n equals 3 state, you could have a 3s, 3p, or 3d. Now, it is allowed to make a transition between 1s and 2p because delta L is equal to 1. And it's allowed to make a transition between 2p to either the 3s or the 3d, but not to the 3p state, because that would have a delta L equals 0, and you would no longer have a permitted transition. Now, you can have forbidden transitions, and they have other rules. There are other rules that apply for the non-dipole transitions, but we won't go through those as they're not necessary. You can just take our word for it. Now, in terms of nomenclature, it's worth just making a point that forbidden transitions are written with a bracket around them. So something like that implies a forbidden transition of the hydrogen atom in its ground state, where the Roman numeral 1 implies its ground state. A permitted transition of hydrogen 2, for example, would be ionized hydrogen, and that would be a transition that would be to the n equals 2, or to the ionized state, sorry. So you could have permitted transitions of ionized, and so on. The key point being that you put the brackets around them. Okay, so where can we go from there? Well, at this point, it's worth recalling let's recall are relationships for emission coefficients and absorption coefficients. And those are from the week 5 lectures. They include such things as the number density for electrons, for atoms that are electrons in the second state as opposed to the first state, is equal to the statistical weights times e to the minus E2 over E1. You might recall this that we wrote out in week 5. And similarly, we've already talked about relating the Einstein B coefficients with the statistical weights. So from those, we can pull together a set of relationships that describe the absorption and the emission coefficients for a few different types of transitions. And we're going to work through in order to describe the transitions for both bound-bound transitions, which is where an electron remains inside the atom, as well as bound-free transitions, where the electron starts inside the atom and then is completely ionized as part of the transition. Before we go on to those, I want to just finally point out some relationships between oscillator strengths. We can relate the so-called Thomas-Reike-Kuhn rule, which relates the individual oscillator strengths, where the final state is equal to 1, integrated all the way up to infinity. The oscillator strength as written out in terms of its initial to final. So this mechanism of writing this is just saying that this is equivalent to an FIF, but I'm writing it for each one of our different states. So this is integrating over a number of electrons, number of bound electrons. And that can be going in either direction. Where any is the number of bound electrons. So this tells us that for a many electron atom, there is a certain set of limits to the oscillator strengths, that their sum of all of the oscillator strengths for the various different states that the electron could be in has to be equal to the total number of the bound electrons, and it distributes the oscillator strengths about them. Now that sort of makes sense. It just suggests that you have a number of different electrons, you put them into the right places, and you add up with the total. This holds for most atoms, regardless of the polarization state. And we can also write for hydrogen a simple relationship relating the statistical weight of the ground state to times the oscillator strength of the transition from the level 1 to level n, whatever n may be, is on the order of 2, sorry, that should be 2, not z, 2 to the 9th power over 3n cubed, electron charge to the minus 2 over electron charge to 2, which is just because it's a simplification, and it comes out to being something like 3.11 over n cubed. Just gives us an indication that depending upon the level, for much higher levels, the product of the oscillator strength and the statistical weight decreases. And we can work through from there to derive a number of other properties of the emission process, which we'll do in our next lecture.